Hello, Tim. Thank you very much for your nice presentation and very informative. I'm from Imperial College London. I'm very interested in the FSI part of your research. My question is, how do you consider the collision of these blood cells together? What model do you use? And how that model would affect the final result as this very thin, narrow area, and that can affect the colliding together and like those kind of stuff.
Yeah, that is a very important question, and it's also, I would say, the most frequently asked question I get. The short answer is that there is no good model for that at this point. What we have is a repulsion force, a short-range repulsion force between red blood cells. Fortunately, in the microcirculation, if you look at the images you can see here, the hematocrit is actually much lower than in larger blood vessels, and that is because you have the Faraeus effect, where the red blood cells move much faster because they are closer to the center line of the blood vessel. They move much faster than the average blood flow. But due to the conservation of mass of blood plasma and blood cells, you actually have a dilution of blood cells in the microcirculation. So fortunately, we are talking about typically 20% hematocrit or something at the scale we are interested in. And at that hematocrit, cell-cell collisions are not really that important. I mean, they occur from time to time, but I believe that a slightly different treatment of cell-cell interaction, unless we talk about aggregation of cells. So that's a different thing, right? Let me say something about that in a minute. But if you change the details of the cell repulsion, it shouldn't change the outcomes. Now, about aggregation, just a short comment. Red blood cells should not aggregate under normal flow rates. They will aggregate if there is basically no flow or no shear flow. But we are talking about relatively high shear rates here in the microcirculation, where the natural aggregation is not really observed. There are certain diseases that cause clusters of red blood cells to form. For example, malaria infections can lead to that kind of behavior. And then, of course, we're talking about a completely different problem. But I think that was also not your question. So for normal blood flow, where the blood cells themselves are not diseased, the cells do not really interact with each other than hydrodynamic interactions. And hematocrit is sufficiently low. So I think that the interaction is not important here.
Thank you very much.
Okay. Peter, do you still have the question? Because your hand is not raised anymore.
I had exactly the same question, but in fact, I'll also maybe ask you, Tim, if you, I very much enjoyed your talk, thank you. You mentioned that you have an efficient parallel implementation without going into massive amount of detail. How do you organize that? Is each step in the coupling separately parallelized, or do you try and organize the parallelization?
So what we have is we have a sparse geometry solver, first of all, which means the dead volume is not considered in the simulations. If you look at the slide in front of you, for any of the two geometries you can see, only the lattice nodes that are inside blood vessels are actually in the simulation, which saves a lot of memory, of course.
Okay.
But this makes also the parallelization strategy much more complicated. We have some kind of, I cannot really answer the question in detail because other people have developed the parallelization of the code. But essentially you have a decomposition algorithm at the beginning that gives each rank a certain number of connected area of lattice nodes. And red blood cells are treated in the way that they are maintained by the rank their center is physically located in.
Yeah.
And of course, you will have situations where you have overlap between red blood cells and other ranks, and there you have to communicate the surface or partial surface of the red blood cell with the neighboring ranks.
So as the red blood cells move, you have to effectively redistribute the data amongst the processes.
Yes. Yeah. So what's happening if a red blood cell moves, let's say from one rank to the other, it packs itself up, sends a message to the neighbor, and the neighbor takes over.
Sounds interesting. Presumably I can find more details of that somewhere?
I think you should definitely get in touch with me, and we can have maybe a one-to-one call, and I can tell you more about that, or via email. So drop me an email. I'm very happy to chat with you.
Thanks, Tim. Yeah.
We have a question in the chat from David Buckley asking, how do you pick a flow rate at the arterial entry to the tumor?
Okay, if I go back to this example here, for an example, here you can see there's a flow rate specified or velocity specified. What we know from the literature is for a given diameter of a blood vessel, we have a rough idea what the blood velocity is in that geometry. What you can do is for a tumor, I mean, we have not simulated entire tumor geometries, but in principle, what you would have to do, you would have to identify inlets and outlets, impose, for example, known pressure values or something that is known from the literature, or you could change the velocity in a way that you recover what you see in experiments. But in the end, experiments will tell you what the velocities are. Normally, what we do is instead of using arbitrary values, because it also determines the deformation of the red blood cell, faster flow means higher deformation, which changes the behavior. We look at the literature and see what are typical flow rates people have reported for that particular geometry.
Thank you. Next question is from Eva. Eva, you want to ask your question?
Yeah, hi, thank you for the talk. I have a question regarding the viscosity of the blood. So when in some vessels that there were some cells that they were just coagulating, or in some of the examples it just stuck as well. So would that affect the viscosity? And if it does, do you need to have a different constitutive law for the stresses?
Yeah, that's a very important question. I usually don't think in terms of viscosity. Viscosity is an effective property of a medium that is basically sufficiently homogeneous. Okay, forget about what I said. But for me, viscosity is an effective property of a liquid, which is a good idea if you have some kind of a smooth suspension where you average over enough particles. In the blood vessels here, we cannot do that. So what we can say, of course, the viscosity of the blood plasma is basically constant. I think there's no debate about that. And the viscosity inside of the red blood cells is also basically constant. What you are asking is, what about the effective viscosity inside a given branch, inside a given vessel? And viscosity is not really a good idea for that, a good quantity. What you should do instead is think in terms of flow resistance and fluxes. And then, of course, you can define an effective viscosity, but talking about viscosity in this case, I find it a bit, it is trying to give a homogeneous property to the blood that you don't have. And in fact, you don't really need a viscosity per se. You can just work in terms of resistances, and which is much more natural to think about, right? You try to push something through a branch and you have a resistance and you measure a given flow rate. And these are observables basically. So you don't really need viscosity, but of course you can define an effective viscosity, and then you can ask, how does it behave? And there is, for example, the Farrar-Lindquist effect that you know. And these viscosity models may be useful if you want to have reduced order models where you replace your suspension by just a liquid and you put the liquid in a network and you want to know for a given branch, what do I have to do with the liquid in order to match what I have on the microscale. Then it makes sense to give a specific viscosity to that. But typically we don't think in terms of viscosities. We think in terms of resistances and fluxes.
That makes more sense. Thank you.
So we have a question in the chat from Kate Fraser. Question is, there are lots of other situations where the cell-free layer is important, for example, in blood contact in medical devices.
Oh yeah.
Is there anything you have learned from your simulations which you could use in reduced order models of other blood problems in general?
Yeah, just for context for the audience, if, for example, if you have blood oxygenators, then you need to make the red blood cells get the oxygen, right? And this means you need close contact between the membranes, artificial membranes that carry oxygen, and the red blood cells. But if the red blood cells don't get close, there will not be a very good oxygen transfer. So what you don't want to have in these devices, you don't really want to have a cell-free layer. But if you come up with artificial geometries that look more like a capillary network, you get a lot of clogging, which you don't want to have, right? It's a compromise between having smooth operation of your device over time without clogging and good oxygenation properties. And the short answer is no, we cannot really say a lot about that at this point, but it is definitely part of our EPSRC project, because you can think about artificial placentas, right? And in an artificial placenta, you have to consider that. So that is definitely within the remit of what we want to investigate over the next 3 years or so. And I think in the future, let's say in a few years, you will have much more knowledge about that particular problem. It's a very important question.
Okay, thank you. There's another question from Amiral.
Yeah, hi. Thank you for the talk. It's very interesting. I just have some question regarding the HemLLB. So as I understand, it's mainly block structured. So how do you resolve the curvatures of all the blood vessels? And does it matter whether you're using stair step or do you use some kind of interpretation?
Yeah, that's also a good question. We have different boundary conditions in place. For example, Buzidi, which is an interpolated bounce back scheme, or staircases. There will, of course, be an effect on the details of the simulations, but we found that curved boundary conditions usually work relatively well. If you have very specific questions, I suggest we take this offline, and you can drop me an email if you want to know more about that. But there are different boundary conditions available for the solid surfaces in HemLB.
Okay, I'll email you. Thank you.
Okay. Can I ask one question? You got to slide number 24 that you said that you do not have enough time to explain why it's not only the diameter of the...
24 or 25?
It was, I guess, it was the slide where you were showing if the diameter of the vessel, what would be the contribution of the diameter, and there was no correlation with that, but it was a clear correlation with the Q star.
Yes.
Just briefly, maybe explain a bit.
Yes, so the main determinant that tells us how many red blood cells go into a given branch in a bifurcation is what is the overflow going into that branch. So you could, let me go one slide farther. If you look at figure panel A, you see a dotted line, which is the diagonal line. And on the axis, you can see the normalized flow rate of blood, which is the total suspension. And on the y-axis, you see the normalized flow rate of red blood cells in a given branch. And completely naively, you would expect that if a given fraction of blood goes into one branch, exactly the same fraction of red blood cells should go into the same branch, which means you don't have any enrichment or depletion of red blood cells, right? This is what we would expect for a macroscopic suspension where we have no confinement effects, where we don't have segregation effects. The data points here show that we have a deviation from that behavior, and it's a very, very important deviation. It's not random noise. You can see there is actually, there are principles behind that. So you can see if you look at the blue data points, we are looking at bifurcation data. So for each bifurcation, you have always two child branches. And normally one of them, in a real geometry, one of them will be larger, which is indicated by L, and these are the blue data points. And one of them will be smaller in terms of diameter, indicated by S, and these are the red data points. And you can see that the vast majority of the larger branches receive the biggest fraction of blood. So if you look at the x-axis, Q blood star, it gives you the ratio of blood coming from the parent branch going into that child branch. And the maximum is 100%, obviously, right? So you can have between 0% and 100% of the blood going into one given branch, and the second branch will get exactly the balance. Both together will carry the entire flow, obviously. So you always get pairs. You always get pairs of data points. And what you can see is that there's a very clear trend that the larger branch will get more flow, which is somewhat to be expected, but not always. You can see that sometimes the larger branch gets actually much less flow. And that has also to do with what the pressure drops are across the branches, because we're in a network. And you don't know a priori what the pressure drops are if you just look at the geometry. So if you just look at a snapshot of the network, you cannot really tell what is the pressure drop between two bifurcations compared to the pressure drop of two bifurcations that are nearby, right? And you need to know all this in order to work out what the fluxes actually are. In our case, the simulation is giving us that, but you need to run the simulation in order to get that data. And you can see that branches that tend to have a higher fraction of the blood share, so basically the ones here, they have an overproportional high ratio of red blood cells going in. If the red blood cells were exactly split in the same way as the blood itself, all data points were exactly on the dotted line. But you can see that there's a tendency, if you have a high throughput child branch, it usually gets even more red blood cells than it should get naively. And if you have a branch that receives less than 50% of the parent branch's flux, then it will get even fewer red blood cells than you would naively expect. And the data is again shown in different figures here, B, C, D, and E, which I could explain it now, but it would take too much time. But you can see that these curves are not straight lines, so they are actually curves. And the behavior of the suspension is captured, the physics of that is captured by the shape of these curves. And you can see that the data points are actually well matched by the model that we have here. Naively, you would have just a straight line between 0, 0 and 1, 1. And the key take-home message for everyone here is, this is not the case. You need to consider that in most cases, red blood cells are either depleted in a given branch or they are enriched. And in a network, this can have profound consequences because you have a hierarchy of bifurcations. If you have one bifurcation after the other, you can essentially get a plasma vessel where you don't have any red blood cells left. And that blood vessel is dysfunctional because you have a blood vessel without any oxygen carrying capacity. So what is it good for? And the human body has some kind of design rules where ideally you should find red blood cells in all capillaries, at least from time to time. And in tumors, in particular, this may be completely different because the structure of the blood vessel network is regulated by completely different mechanisms, which went out of control, essentially.
Okay, thank you very much. Question from Virginia. Out of curiosity, is there any similar model related to monocytes instead of red blood cells?
That's also a good question. Red blood cells form the biggest particular species in blood, 45% of the volume, and monocytes and other leukocytes or white blood cells, they are less than 0.1%. And therefore you would expect that the distribution of any other particle in blood will be to a large extent determined by the red blood cell distribution, but it may not follow the red blood cell distribution. So if you look at blood platelets or white blood cells or bacteria or whatever you have in blood, these particles may be distributed differently than the red blood cells. And it's currently unclear how this is all playing together. So the short answer is there's probably something that could be said about white blood cells, but it is currently not known.
Okay. There's another question from Noshin. How good is the comparison between the Lattice-Boltzmann model and the finite volume model for blood flow modeling?
I don't fully understand the question because there's no comparison between Lattice-Boltzmann and finite element. Both together are part of the model. Maybe I misunderstood it.
Well, I don't know, he or she is asking between the Lattice-Boltzmann and the finite volume model.
Sorry, finite volume. Okay, sorry. Right. Finite volume, of course, is a different fluid solver. And It really depends on the problem. There are applications where finite volume methods are more accurate than Lattice-Boltzmann, and there are methods where Lattice-Boltzmann is more suitable. And I'm not aware of many works where people have used finite volume methods for blood flow. I mean, it is definitely used, but I would say as long as your Navier-Stokes solver works well, for this particular application, most of the uncertainty is actually caused by the red blood cell model itself. So I would say if you replace the Lattice-Boltzmann by a finite volume method and you make it workable with your complex geometries, probably you would get very similar results.
Thank you. There's another question from Laura. Are there any models that consider the effects on the bloodstream distribution caused by agents such as high or low density cholesterol, high blood sugar level, etc.?
I'm not aware of anything. Of course, you could investigate what is happening if you. I'm not aware of that in modeling. At some point, I started to look at what happens to smaller particles, like LDL particles in blood flow, but we didn't make a lot of progress in the meantime. So I think there's definitely a need for understanding what is happening. It's similar. It's related to the question that we heard earlier about white blood cells in blood flow. I think that the red blood cells are the most important particles that will affect everything else that is moving in blood. But then again, other components may affect the way red blood cells behave. So what happens, for example, if you have an inflammation in the body, will it change the properties of red blood cells? So you may have to take into account an interplay of different components rather than just saying they do what the red blood cells do. It's highly interesting and relevant, but the modeling these days is not able to do this, not reliably at least.
Okay, thanks a lot, Tim. There were many questions, I guess.
Thank you very much for your questions. It was great to speak to you, and thanks for your attention.
Well, if there are no other questions, I just thank Tim. Thanks a lot for the interesting talk and answering all the questions. And thanks to all the people who joined the seminar.